Today we're going to learn about two important theorems. There is a rule of thumb to follow in this class. If a theorem has its own name, it's really important. You get two of them today. They're not that bad. There's just a little bit of conceptual stuff to deal with. So the first one is Rolle's theorem, named after a French guy named Rolles. So we'll talk about that a little bit. And then we're going to talk about MVT, the mean value theorem. That is a very, very important theorem. Rolle's is important too, but mean value theorem is much more important. And you should be able to count to 10 in German. Anybody?
1, 2, 3,
Zup.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Well done. Let's give it up. If you cannot do that, he'll be giving lessons later.
That's all I know. That was 1 to 10.
That's it? You stop at 10?
No, that's all I know.
Do you know any other German?
No. I had a German CD and I listened to how to count from 1 to 10, and then I got bored.
We all know a little bit more German. It's just not really understood.
Why did you have a German CD?
I found it. Apparently my dad was trying to learn German. He works for a German company, so.
Oh, so he's learning German.
Yeah.
All right, that's understandable. So it was like a Rosetta Stone type
Yeah, it was
thing.
that sort of thing.
And you got only 1 through 10.
I got 1 through 10.
You didn't learn like where's the bathroom or
No.
no. Ich habe einen Geburtstag. No.
Say it again.
Ich habe einen Geburtstag. I have a birthday. Ich weiß es nicht. I don't know. You got to learn that, especially if you're taking German in college.
Wait, what is I have a birthday?
Ich habe einen Geburtstag.
Just I have a birthday.
I have a birthday. Yes.
I feel like you could say the most fancy thing ever and it still sounds like.
Still sounds like you're coughing up phlegm. That's how I feel about the French language. German is a little harder and more succinct.
It is so offensive.
I'm sorry.
I think it's French is a
Many people think that. I disagree.
It's just like, okay, it's not as bad as German.
It's hard to speak German and not sound like you're yelling at somebody. There's no happy German. Right? It's not like you. Yes, John.
Can you whisper in German?
See, even then you sound intimidating.
Yeah, it does. It does sound like you're threatening somebody.
I hope it's all right.
Rolle's theorem. There's the calculus speak. This is important because it's in a colored box. And there is a hypothesis and a conclusion for this. The problem with Rolle's theorem is that you have to make sure the hypothesis is correct before you move on to the conclusion. I'm sure you all remember that from geometry logic, right? No. Okay, let's move on. The part before the comma, also known as the if part, is the hypothesis. That has to be satisfied before you can move on to the conclusion.
Is there English?
Yeah, but you want to write that down. We're going to go through this in its individual parts so that you understand it. First things first, f has to be continuous. Okay? We have a function that's continuous on the interval, including a and b, and differentiable on the entire interval except for a and b because it's not differentiable at the endpoint. Okay, so that's the first part of the hypothesis. That's what you have to have first. It's got to be continuous and differentiable. Then the more important part is f of a has to equal f of b. What is that in English? Say again?
The y's have to equal each x.
Correct. Yeah, good.
What do you say?
He said the y's have to equal each other on each end.
So like
If that is satisfied, then f prime of c has to equal 0 for at least one c in the interval. What does that mean?
At 1 point.
Which means what? Good. Did you hear that?
Can you repeat that?
The derivative has to equal 0 at some point, which translates into there being at least one point where the tangent line is horizontal. There's an easy way to remember this theorem. Okay. You start on level ground. That's supposed to be level. You start at this point here. You're going to end on this point. Okay, again, level ground. That satisfies the hypothesis. I'm going to go from the first point to the second point up this hill. Okay? And I'm not just going to go up the hill. My life has been made difficult. I have this giant ball that I'm going to roll up the hill. I'm rolling a ball up a hill. Are you with me? What the theorem says is if I start at level ground, I roll a ball up a hill, and then I go back to level ground, somewhere along the way I've got to hit the top of the hill. Does that make sense?
Yes.
Okay, good. Now, what the theorem says calculus-wise is not only will you hit the top of the hill, but you could hit the top of many hills. The theorem says it has to hit at least one top of the hill. But your path could look something like this.
That would be fun.
That would not be fun. Okay? That still satisfies Rolle's theorem. All Rolle's theorem says is there's got to be at least one point. Yes, sir.
Rolle's theorem, rolling. Did he do that on purpose?
Yes, that was intentional. That's how you remember Rolle's theorem. You're
He
rolling the ball up.
himself
a hill.
his theorem just to.
Yeah.
He changed his name, yeah. His name was actually Bill Jenkins. He changed it to Michel Rolle. That's the best I can do at French pronunciation. I'm sorry.
That was pretty close.
Michel? Right, is that right?
But would it be like with the two L's? Would it be something like a Y?
Right?
Or is it-
He's only got one L in his name. He's only got one L.
It's weird because sometimes two L's will turn to like a Y sound.
In French?
It'll happen Marseille.
Yeah.
You sure that's not Spanish?
It'll happen.
Oh, I'm not here.
Like I said, Marseille.
I mean, they're related languages, if possible.
Doesn't have to be up a hill. It could be down into a valley. So start here, end here. At some point I have to hit a bottom or a bottom. It's easier, I think, to remember, though, thinking about rolling it up a hill.
You think positive?
Right, right. Half full, half empty kind of thing. Okay? That's what it says. Whoops, wrong button. Let's try that again. There we go. Before you can apply Rolle's theorem or even talk about Rolle's theorem, you have to satisfy all three of those initial conditions. It has to be continuous, it has to be differentiable, and you have to start and stop at the same point, same y value. So when you're applying Rolle's theorem, the first thing you're going to do is check what f of a is and check what f of b is. If f of a and f of b are different values, you're done, no Rolle's theorem, move on. If they are the same, then you can proceed with Rolle's theorem. Make sense? Yeah. Good.
So you're just finding where the tangent equals 0?
Rolle's theorem doesn't even tell you where it is. It just says there's got to be one. You got to go find it on your own. He wasn't a huge problem solver. He just said, look, between A and B, it's got to happen somewhere. I don't know where. You go deal with that on your own. I'm just telling you it's going to happen.
So when both the y values are equal,
Mhm.
you know that you have to like find
Right. And how would you find those points? Take the derivative set equal to 0. Yeah, same stuff we've been doing already. We good?
Is it possible for it to be 0 the whole time?
I'm sorry? Who's talking? Is that you?
Yeah, is it possible for it to be 0 the whole time?
Could be. Your hill might be low enough that you're rolling it just from point A to point B. And then you have a whole bunch of points, or an infinite number of points. Okay, so let's show how this works. I've got a function, x squared minus 3x plus 2. And I want to show that there's some point on the interval from 1 to 2 where we'll hit a max or a min. And we're going to do it without graphing, because that would be cheating. Is that function continuous?
Yeah.
Yes.
How do you know? Not even a parabola, it's just a polynomial, right? So, is it differentiable? Yeah, there's nothing in that function that would cause it to be non-differentiable. There's no jumps, there's no gaps, there's no weirdness, there's no cusp, anything like that. Okay, so then we proceed. Well, I think I skipped a whole bunch here. Let's go back. I think I got to do the grunt work here. I need to know what is f of 1, and I need to know what is f of 2. What's f of 1?
0.
What's f of 2? 0. Okay, so we've taken care of the hypothesis. The function is continuous. The function is differentiable. The starting and stopping points are at the same y level. So therefore, Rolle's theorem applies. That's pretty much how you're going to apply Rolle's theorem. There's got to be some point between 1 and 2 that the derivative will equal 0. Okay? That's where Rolle's theorem stops, and then we can move on and start doing all kinds of things like figuring out what the value of c is. We take the derivative, set it equal to 0. Get rid of that. Over here. I just said that. And then we can proceed from there. Okay, so now we need to find c. And finding c is the same stuff we did yesterday. Take the derivative, set it equal to 0, and solve. And therefore, x is equal to 3/2. Good. What we haven't talked about yet is what's happening at 3/2. All we know at 3/2 is that it is going to be either a max or a min. We don't know which one yet, and we don't really care at this point in time. We just know that there's something special happening at 3/2. Question?
Since it's a parabola, would that make
It is the vertex. That's why I picked an easy function. Depending on how nasty the math gets, you could get a whole bunch of different points. Because understanding Rolle's theorem is easiest to think about if you're going up and down a hill. But again, like I showed you, that hill can have a whole bunch of peaks and valleys. This one happens to only have one. Okay. Are we good on Rolle's theorem? Yeah.
Can you have it on like a point graph or just curve?
You can't have it on a pointed graph because it would be non-differentiable. Okay. That's a good question. And that's why we don't just care if it's continuous. We want to make sure it's continuous and differentiable. Like, think about a graph that came up to a point like that. Yeah, you're not going to be able to roll the ball up that hill. Okay. Mean value theorem, MVT, very important. Okay, so the mean value theorem says, well, let me back up. The reason we needed a Rolle's theorem was because we used Rolle's theorem to prove the mean value theorem. The mean value theorem is much more important than Rolle's, but again, we need Rolle's to get the mean value theorem. Same scenario. You have to establish that the function is continuous and differentiable. We don't care so much that we're starting and stopping at the same point. What it says is that the derivative has to be equal to that stuff on the right. What is that stuff on the right? Does that look familiar? All right, let's draw a picture to answer that question. I've got some function. Let's take a nice parabola here. Here's A, here's B. The left side of the parabola is, or the left side of the equation is the derivative at some point C. So that would be the slope of the tangent line. What's going on the right side?
I have a question.
Sure.
C is any point where the derivative is 0?
Which would be represented how graphically?
Slope?
Good. This is the secant line. That. It's a slope calculation. It's a slope of that line, or that segment. So what the mean value theorem says is that somewhere in this interval from A to B, there's got to be a tangent line that has the same slope as that line. In this case, it would look something like that. And I've got some better pictures to show you in a second. That point right there would be what we call C. That's where it happens. Now notice, that's not horizontal. It doesn't have to be horizontal. It's parallel to that other line. Okay, so we take Rolle's theorem, which Rolle's only cares about horizontal lines, or horizontal tangents, and we change it in the mean value theorem where those lines can have any slope as long as they match. Okay, so let me show you a picture here. There's the buzzword that you're going to use for MVT. The slope from calculus has to be equal to the slope from algebra. That's the way that you remember it. What will eventually get burned into your brain is anytime I say MVT, your immediate response is going to be slope from calculus equals slope from algebra. The slope from calculus is the slope of the tangent line. The slope from algebra is the slope calculation, which is the slope of the secant line. Are you with me? Was that a no or a yes? Yeah. Yes, that was a no? Yes, it was a yes. Okay. So there's a picture. That one's a little better than the one I had. I go from A to B. This line has a slope calculated by the right side of that equation. This is the tangent line that we calculate from the derivative. So we're going to be doing two things here. Calculating a slope from algebra and calculating a slope from calculus. Depending on the problem, one is usually easier than the other. Yeah.
Why are you not taking the like derivative from when it's equal to 0?
Because Rolle's theorem is only concerned about it being equal to 0. This one, I want to take the derivative when it matches that one. Because I want these two to be parallel. Okay? And that's a big difference between Rolle's and mean value theorem. Okay, so here's our example. I've got a parabola, just like I had in the other picture. And I want to find the mean value theorem for that function from 2 to 7. What question am I going to ask first? I'm sorry? Is it continuous and differentiable? Is it? How do you know? It's a polynomial. Good. That takes care of it. Now, they won't always be polynomials. It won't always be that easy. And also notice that we only care if it's continuous and differentiable on the interval. So, for instance, if I had a function, let's suppose I had this. And I asked you about the mean value theorem over the entire graph, we would have a problem because it's not continuous nor differentiable. But if I make it only go from 1 to 10, now it works. That function is continuous and differentiable on that interval. Okay, so the important part is to remember we're talking about the interval, not over the entire graph. The parabola here doesn't matter because it's continuous and differentiable over the whole thing because it's a parabola, it's a polynomial. Okay. So that's what we talked about already. You have to check this at the beginning of your mean value theorem. You need to say the function f of x is continuous and differentiable because it's a polynomial, because it doesn't have any gaps. You've got to explain that first before you can proceed. Is that too bright? Do you need me to close the blinds a little bit? We're good? Sun's good? Can you see the board still? Okay, good. All right, so on the left first, we've got the slope from algebra. So find f of 2 and find f of 7. Now you have an x coordinate, you have a y coordinate. You have an x2 coordinate, you have a y2 coordinate. On the right, I found the slope, or I found the derivative actually. I'm going to find the slope from calculus in a second.
Yeah, could you?
Can't see? Okay.
Thank you.
Better? Okay. I'm assuming you can do the slope calculation over here, yes? Go ahead, I'll wait. Make sure you do right side up and not upside down. What's the slope over here? 13. Okay?
15.
That's why I said 15. 15?
Yeah.
Oh, yeah, 75 divided by 5. Okay, good. That's 15. Now, what does that mean? That means that if I connect the points 2 and 7 on that parabola, it's going to have that secant line is going to have a slope of 15. I want to find the spot where the tangent line has the same slope. So do I plug 15 into that derivative, or do I set the derivative equal to 15? Set it equal, correct. So there's the slope calculation. I come over there, I set it equal, solve for x, and I get 4.5. So there's two parts to this. One is understanding what's going on, and the other one is being able to solve it. Here's the way to solve it. Again, slope from algebra has to equal slope from calculus. Understanding what's going on is different. Okay, got a parabola, I connected two endpoints on the interval, I have slope of a secant line. I want to figure out where along that parabola is the slope of the tangent line going to match the slope of the secant line, and that happens at 4.5. Okay, we good? Another example. And this is what I talked about earlier. Even though the entire function isn't continuous and differentiable, we're only dealing in an interval from 1 to 4, which it is continuous and differentiable over that interval. What's f of 4? 4. What's f of 1? 1. So therefore, what's the slope of the secant line? 1. Now what? Take the derivative, set it equal to 1, and solve. Which looks something like, where are we at? There's the 1 that we did. Here's the derivative of that. Set it equal and solve. So what's x? Plus or minus 2. It happens at 2 different points.
Can you go back a slide?
Sure. Let me ask a question first before I go back. What's wrong with that answer?
They can't
John?
-2 is
So therefore, what do we do with the -2? Get rid of it. There's only one answer, and that would be 2. Okay, and you want to go back? Okay, good.
Will we ever have it where there can be 2 solutions inside the interval?
Yes, there could be 2 solutions. It could be no solutions. Let's suppose you solve this and you get values. In this particular problem, let's suppose I got values of -5 and -2. Neither one of those answers are in the interval, so that means that it doesn't ever match the slope. Okay? And that's a little persnickety thing that shows up occasionally. You got to check to make sure that your answers fit into the interval that you started with. Not so bad. That's actually a bridge. That's the fancy mean value theorem. That's a bridge in, I think it's in China, where somebody thought it would be a good idea to put the mean value theorem on a bridge. I don't know if I'd say it's cool, but it's interesting.
We know what I would do.
I don't know how that came up. Maybe I Googled mean value theorem or. Yeah. Next thing I'm gonna search is mean value theorem on a dog and see if somebody's carved the mean value, or mean value theorem tattoos. That would be a good one. What do you got?
Go back one slide.
Is there a more,
No, that is it.
No, I don't.